Hello, I'm Karl Zielinski. Welcome back to Make Games Using Odin plus Raylib. This is the sixth and final episode of this series. And I thought today that we will look at some level editing basics. The game at the end of episode 5 looked like this. You are this cat that is running around and you can jump up on these blocks. These blocks are currently hard-coded. Their position, where they are in the world, is hard-coded. So I thought today we will just make a tiny sort of level editing thing where we can place these blocks wherever we want them to be from within the game. On the right here I have an outline, as usual, of what we will be doing today. So we will first add some kind of struct to contain our level, and then we will make it possible to place and remove blocks, essentially the level editing part of it. And then we will run into some interesting memory issues with memory leaks that we will look at and how you can handle that. And finally, we will also write and load the level to a file. And then after that, it's goodbye for this series. But I will talk a bit also about what series are coming up and what I will do on this channel when this series is done with regards to making games using Odin and Raylib. So let's jump straight into it. So add a level struct. Currently in the game, the platforms live in this sort of list here. There's 3 platforms that are defined like this. And in order to make the level editing the process of writing the code we need for the rest of this episode, I want to introduce some kind of struct to keep everything for our level inside, sort of our little game world. So up here, just before the main proc, we will put in a new struct called level. And this level struct, inside it, we will have a field called platforms. And this field will have the type, and I write like this, dynamic rl.vector2. We've seen this kind of 2 brackets before without the word dynamic in it. We've seen it like this kinda down here. This is just a list of rectangles. The thing is, when you have it dynamic like this, means that you can append and remove items from it, so it can grow dynamically. It's not fixed how big it is. And that's good for later when we want to do our little level editing, because we will add platforms and remove platforms. A difference you might notice here is that I say rl.vector2 here and rl.rectangle here, because all these rectangles actually have the same size. So I thought it would be better to just only store the position, which is essentially a vector2, which is 2 numbers. So instead of having all these rectangles explicitly written like this, I thought we can just make a little procedure called platform collider that gives us the rectangle for a platform at a specific position. So we can write like this, platform collider, just above the main proc here, where platform collider is a procedure, and this procedure will take as input one vector2, and this will be the position of where the platform is, and it will return an rl.rectangle. So, and this is sort of the full rectangle that contains both the position and the size of the rectangle. So let's say that this procedure then returns, and it will return a rectangle, so we can just write brackets here. This is implicit, like you just write these 2 brackets, and then whatever is between these 2 is the initialization of this rectangle, what it should contain. So you don't need to write rl.rectangle here, because it knows that from the return type here. So then we can write just post.x, post.y, and currently all our rectangles are 96 by 16, so we just hard code that in. So the 4 fields of a rectangle is x position, y position, width, and height. So that's the procedure we need for that. And now we can go down here and we can replace this platforms list with a level. So instead of platforms, we will write like this. Level is a level, and it contains a list of platforms, and we will just take these numbers here. I can just key them in -20, 20. So I'm just copying these over. 90 minus 10, and then 90 minus 50. And now we can delete this. So this just creates a new object of the type level struct. And then when it initializes it, it says that the list platforms, the dynamic array platforms should, when it is created, should contain these 3 things. And these 3 things are just vectors of the positions where we want the platforms in the world. Now we just need to scroll down to where we actually use the platforms, where we check the collision here, and where we draw them down here. And we need to make sure that all this code works properly. So first thing is that this for loop here, which loops over the platforms, used to loop over just this platforms variable. This list of platform now lives inside the level. The second thing is the platforms list is no longer a list of rectangles. It's a list of vector 2s. It just points like the positions of the platforms. That's why we added this procedure up here, platform collider. So we can use this procedure to calculate the rectangle given a position, since all our platforms have the same size. So we go down here and we write platform collider. And then we just send in the platform here. And then when we've done that, we can scroll down to this code here for platform in platforms, where we actually draw the platforms, and we can type level.platforms. And then the final thing here is that platform is now just, like I said, it's just a vector 2. And what draw texture v expects is actually just a vector 2, the position to draw the texture at. So instead of constructing a vector here from x and y, this used to be like this because we used to have a rectangle. So you took the x and y out of it to construct a vector. But now we can just use the vector straight up. Now if we press F7 to try to compile and run our game, I get an error. It's up here. What happens is that we're just missing a comma on this line here. In Odin, it wants a comma. If you separate your the elements of initializer list like this by new lines, so you have everything in new lines, then it wants a comma after the last one. You don't need it if it's on a single line like this, but if it's on separate lines like this, you need a comma. And that's just nice because often when you come back to code later to add a new thing to a list, you forget to put the comma in to the currently last one, so then you get that error then instead. So now I'm just leaving clean code around that's easy to change instead of, having people get the error later when they add in something. So I think that's just nice. Now if we compile and run our game, the game looks like this. This looks like before, but now it is using this list of platforms within this level struct. So we are ready to put in our little level editing. So let's do that. Let's make it possible to place and remove blocks. First thing we need is a variable that tells us, are we currently editing or not? We're currently editing the level or not. So I will add a bool that's false here called editing just before the main game loop here. And then I will go to the bottom of the game loop. And just before end mode 2D here, I will put in my little level editing code. If rl.is key pressed .f2. And what this code will do is we'll just enter and leave the editing mode. So we will just put the game into a mode where we are currently editing this list of platforms essentially. And the thing we do in here is we just write editing equals not editing. That just flips. If the editing is true currently, it will become false. And if it's false, it will become true. So that way we can jump in and out of the editing mode. So then just after that code, I will make a new if statement that is just if editing. And here we can do all the special stuff we want to do for when you are in this editing mode. And the first thing we need to do is to know where is the mouse cursor currently, because we want to place things using the mouse, right? And we are not so interested in where it is on the screen, because the player can move around the camera by walking around. So we are interested in knowing what is the sort of world position of where the mouse is. What point in the world does that represent? And that's also what we want to use for placing our blocks or platforms in the world. So I will write this: mp equals rl.getScreen to world 2D. This is a function in Raylib that takes a vector2 that is on the screen and says where in the world is it. And the way it does that is by using the information the camera gives of where you're looking in the world. So we say that we want the mouse position, so we write get mouse position. That's the position on the screen where the mouse is. And then we also feed it the camera. Now this one will use the camera to tell us where in the world does the mouse currently point at. And then we can draw the texture of the platform we want to play. So this is sort of our paintbrush, our kind of cursor of this is where the platform would end up when we click to add it to the world. So we just write rl.draw texture v, and this is almost exactly the same as up here. So we say platform texture, but instead of this position here, which is the platform of where it sits in the level, we want to just show it where it sits, so that it sits where the cursor is. And then the tint is as usual white. We can try running this program now. So here is the cat, and if I press F2, then it will enter this editing mode. And now you see that I have a platform on my cursor. It doesn't do anything yet. I can click all I want. It won't do anything because I haven't written that code. And I can leave the editing mode by pressing F2 again. I can press it back and forth like that. So let's add that code now to place the blocks in the world and also make it possible to remove them. We will start with making it possible to place them in the world. So what we do then is we say if rl.isMouse button pressed, and then we say in capital letters .left, like this. This checks if the left mouse button was pressed during this frame. And what we do in that case is that we write append, and then we write level.platforms, and then we send in the value mp. This append thing here this is the first time we see it in this series. And what it does is that it adds a new element to a dynamic array. So in our level, we have a dynamic array of vector2. And like I said, the dynamicness of this means that it can grow and shrink. So we can add things over time, and we can also remove things. We also want it to be possible to remove blocks. That's a tiny bit more complicated, but what we will do is if rl.isMouse button pressed, all capitals, right, some curly braces. So if the right mouse button was pressed, then we want to check if there is one of these platforms under our cursor right now, and if there is, then we delete it. So what I do is I just loop over all the platforms. So I write this kind of loop here that it's similar to this one where I looped over all the platforms, but I will add one extra thing. So I write p, idx in platform level.platforms. So what this does is that it loops over all the platforms, and for each platform in this list of platforms, it will tell us the position of that platform. But this idx is optional. You see, I don't have it up here. It's optional, and it will tell us which index, which number, at which position in the list this one currently is. And we will use that to delete things from the list later. So essentially, if you look at the initial list here, this one sits at index 0, this one sits at index 1, and this one sits at index 2, so 0, 1, 2. So in order to check if the platform is under the cursor, we use if rl.checkCollisionPointRec. This is a bit similar to the check we did up here. Here we used check collision recs for the gameplay of the collision detection. This one compares two rectangles to each other to see if they overlap. And what this one here does is that it instead checks if a point is inside a rectangle. So we send in the point we want to check, which is the mouse position, MP. And then we need a rectangle to check if the mouse position is currently inside that rectangle, and we use then platform collider P. And then we put some curly braces. So if the mouse position, which is in world coordinates, because of this get screen to world thing up here, if that thing is inside the platform collider, which is also in world coordinates, because it says we're in the world and how big is the platform. If this is true, then here we can remove it. So what we will do now is we write unordered, ordered, remove, and then we write from level.platforms, and then we've sent in the IDX here. And then I will add one more thing, we'll type break here. This is one way to remove something from a dynamic array. There is also an ordered remove. Unordered remove is a bit faster. Ordered remove makes sure to keep the order of how things was in that list so that nothing moves around, while unordered remove swaps the last thing in the list in where you want to delete it and makes it a bit smaller, so it doesn't have to copy lots of memory around essentially. So it will remove, since the index of the one we are currently looking at is this one, it will remove that one here. The break I put here because we are currently looping over the list of platforms, but here we are deleting a platform from the list. So the size of the list is changing while we're looping over it. So this break will just quit this loop, it will just jump out of this loop. Since we've already found the platform we're looking for, we don't need to go look for another one, and continuing to loop just after deleting something from a list can cause quite severe issues. So if we now compile and run the game, we see that we get a compile error here because I have forgotten an ampersand in front of level platforms here. You can see that we have one up here as well on append, and both these need the ampersand because the ampersand will take the address of this platform, which gives append and unordered remove a pointer to the list of platforms so that it can actually modify that memory. So if we now compile and run again, we see this. And if we now press F2, we get our little floating platform. And if I click the left mouse button, then it sort of stays there. And I can jump there and jump up on it. And I can place another one, jump there and jump up on it. And it's a bit funny right now, we can play the game while in the editor. That's quite unconventional, but that's because this is a just simple first example of how to do this. We can leave the editor and run around, we can jump into the editor, put a platform over here, and then leave the editor again, and then jump to that one, put one here, leave the editor, jump to that one. I mean, you could maybe make a game out of being able to put out platforms somehow while playing the game, because I can play the game while being in the editor, so I can do something like this, place a platform over myself all the time. And then of course the deletion also works. We can right click and the platform disappears. So now we've made a simple sort of level editing thing where we can place and remove blocks. Okay, so let's go on a little side quest here. The point 3 is fixing our first memory leak. So the platforms field here in the level struct contains a dynamic array of vector 2s. And a dynamic array can, like I said, grow. And whenever something needs to grow, it will need some memory to use. So the more platforms you place, the bigger this list gets. So it sort of dynamically grows. Yeah, in order to do that, it will ask the operating system for more memory. Then when you do this kind of dynamic allocations, you are expected to return that memory to the operating system at some point. So how would you go about actually finding these memory leaks? Going around your program and looking for suspicious things like this might be tricky. And what I think you should do is that you should use a tracking allocator. So a tracking allocator is something that essentially tells you if you have memory leaks in your program. So we will add a tracking allocator to this program, and it's very simple because Odin comes with a built-in one. So what we will do is we will go to the top of the file here and we will type import core mem. Core is the sort of core library of Odin, and mem is a package in there that contains some nice things for memory management. And then we go back to the main proc here, and just at the top of this proc, we will type track mem.tracking allocator. So we create a new variable of type tracking allocator, and this one comes out of the mem thing we imported up there. And then we say that we want to initialize this tracking allocator. And what a tracking allocator does is that it takes, what an allocator does is that it tells our program how do you allocate memory, how do you get new memory from the operating system. And we initialize this one by saying mem.trackingAllocator_init, and then we send in a pointer to the tracking allocator, and then we say which allocator do you want this tracking allocator to wrap. Now, there is a default allocator in your Odin program, and you can find that one on context.allocator. So whenever you, for example, run append like this, and this platforms list needs to grow, it might use your allocator on the context. It only uses it the first time, and it then stores which allocator it used, and then it continues to use that one whenever it needs to grow again. But in essence, append and creating new dynamic arrays, for example, will use the allocator on the context. So this will make this tracking allocator wrap this allocator. So it still uses this one to do the allocations, but it also saves some information on which line in the program did our allocation happen, so that we can go and find them easily. Finally, we need to tell the Odin program that we want to use this tracking allocator as our actual allocator for doing allocations. So we write context.allocator equals mem.trackingAllocator, and then we write &track. So then we sort of, we replace the thing at context, inside context.allocator. And the context is a special object in Odin that is sent into any procedure you call. For example, when we call platform collider or something else like draw animation up here, the context is actually implicitly sent along. So all code below this line will see the same context.allocator. So this sets up our allocator. It doesn't do anything yet. Well, it does something. It will continuously wrap these allocations we do. For example, growing the platforms list with this extra information about which line it happened on. But now we want to somehow tell the user if a memory leak occurred. So the way we will do that is that we will add some code just below here, and I will write defer. Defer is a word in Odin that makes whatever I write between these two curly braces here to happen when this procedure ends. So this code that is between these two lines actually happens down here when this main proc ends. It's just a convenient way to sort of group, because I create a tracking allocator here, and then I want to write some code here that looks through the tracking allocator and sees if there was any memory leaks. So then I can just write a loop here, and I write for_entry in track.allocation map, like that. And then I write fmt.eprint, like that. And then I write v leaked. I will explain what all this does in a moment. Entry.location, entry.size. So this loop goes through all the allocations that are in the tracking allocator, and if something is in this list when the main procedure ends, then it means that those things have not been returned to the operating system, that memory has not been, as we say, freed. You might also ask, why is there an underscore and a comma here? That's just because this is a map. A map is a thing that contains both a key and a value. It contains two values essentially, and we're only interested in the second one. So we just write underscore here to signal that we don't care about the first one. So we look at the entry of each thing. Then we need one more loop called, that goes like this, for entry in track.bad3array. And we write similar to this, we write eprintf, and we write vbad3 \n entry.location. And then just after this loop, we also write mem.tracking allocator destroy and track. So the contents of this loop sort of this will just print on the screen an error containing this information. It will say the first %v here is replaced with this thing, and the second one is replaced with this thing. So it will say at this line in the code, this amount of memory was leaked. This loop down here is actually not related to memory leaks. It's related to bad freeze, which is if you have some memory and you try to return it twice, for example, so that you have a buggy program that tries to return memory that is actually not allocated, then it will tell you that you did that. And then finally, there is a line here to destroy the tracking allocator. And like I said, all this code will run at the end of the main procedure because of the defer. So if we now try to run this, F7, we get some compiler error, undeclared name fmt, because I forgot to include that. So we go up here, import core fmt. Fmt contains lots of things to format strings and to print strings to the screen. So if we now compile and run the game is like before, but if we close it, then we see that it says in this file, at this line, it leaked 24 bytes. So we go down to line 113, see here, 113, oh, it's this line where I created my list of platforms. Now, if we start the game again and we go into the editor and we place some platforms, leave the editor and then close it, you will see that the error actually moved to line 201, to this line, append. And this is because the first time we did it, we didn't put out any platform. So then the memory allocation happened here, where it created the dynamic array. And the second one, on the second time we did stuff, it happened down here because we appended some platforms, and suddenly the list of platforms couldn't contain, it wasn't big enough, so it had to make it bigger, which essentially means ask the operating system for a list that is longer than the old one, and then copy all the data to the new one, and then throw away the old one. So then we no longer get a leak up on 113 because this one actually returns the memory of the old one, but it makes a new one. So now that we found a memory leak, we know that level of platforms is leaked here. We simply need to somehow return that memory to the operating system. And the way we do that is at the last line here, just before the main procedure ends, we write delete level.platforms. And if we now build and run and close, the error has gone. What delete does is that it returns the memory for the dynamic array that contains our platforms. So I would like just to say something general about memory leaks here too, because I think there's two types of memory leaks. One type is that we have a continuously growing memory usage. So somehow the amount of memory our program uses grows and grows and grows. And then we have the other type, which is that it's something that it's a memory that is allocated once and then not returned, but it only happens once, so it doesn't continuously grow. In this case, if we look up here, the platforms list is here, and it will, yeah, sure, if we edit the level and add platforms and stuff, the list will grow, but it's not gonna continuously grow by just having the program running. It's just when we add things to the list it grows, which is natural. And this is sort of a less bad type of memory leak, I would say, because it doesn't actually matter that much. This delete here at the end, it's not that important, because the memory that your platforms list has here will get returned to the operating system when your program shuts down. So it doesn't matter that much. However, if you have a memory leak that continuously grows just by leaving the program running, then that's quite bad. And you can get something like that by, for example, having an allocation that happens each frame inside the main loop. Perhaps you made some code for doing pathfinding that returns a dynamically allocated array of some information or something, and that memory just is never freed. Then that's a bad type of memory leak that will just make your program grow and grow and grow in memory use. And those are more important to fix, but in general it's just good to make sure the tracking allocator is happy when you shut down, so that you can see those bad memory leaks when they happen, so they don't get drowned out in these lesser memory leaks like this one. Okay, good. Now that we've done that, we can go to the fourth point on our list here, which is writing and loading level to a file. So if you make any kind of level editor, of course you want to save your stuff so that when you start the game up at another point, you can load that level again. Here we will just make something super simple that loads a specific file on startup and saves it out to that same file when you quit. But you can enhance this to make it more fancy if you so wish. So what we will do is we will add some code just before this delete here that takes our level struct and turns it into JSON. JSON is a format to describe sort of human readable data. And it will turn it into JSON and then write that into a file on the hard drive. So Odin comes with a built-in library for reading and writing JSON. So you don't need anything extra to do this really. We can just write here, just after close window, we write if level data, comma, error, colon equals json.marshall. This will take some, for example, struct in our program and turn it into JSON. So we say we want to turn the level into JSON. And then it also expects you to supply an allocator here. Because if we just type like this, then it will use the default allocator. Then we would have to clean that memory up down here. But I just prefer in this case to use the temp allocator. So I can write like this because I can say that the allocate json.marshall first has which object do you want to marshal, and then it has some options, and then it has the allocator. I don't want to specify the options, so instead of writing something here, I can just write allocator equals, so then it will by name say that the parameter called allocator will have some value. So I write context.temp allocator. The temp allocator is a special allocator that's for memory we do not care about in the long run. It will stay valid for as long as we don't free everything on the temp allocator, which I will show you how to do. But it's just a fire and forget type of allocator, because this procedure will allocate memory. And since I don't care about having that memory around in the long run, I use the temp allocator. And you see, we have a funny thing. We have an if, and then we have two variables, and then we set those two variables to whatever this thing returns. So json.marshall returns level data, which is the data the JSON data. It turns the level into JSON, and then it returns an error if something bad happens. That error will have the value nil if nothing bad happens. So we just put a semicolon here, and then we write error equals nil, and then we write some semicolons, some braces. So this is a sort of a very Odin thing here. You can have an if statement that declares some variables and then put a semicolon and then check one of them, which is nice because now we can sort of run json.marshall, assign the two return values of json.marshall into these two, and then check if error is equal to nil, which means there was no error. And then inside this if statement here, we can then use level data and be sure that it is correct. So if it managed to turn our level into JSON, then we want to write that data into a file. And the way we do that is we type os.write entire file, and we say the file name, and we write level.json, and then we say the data level data. So this will take this data and put it into this file. Now, if we were to run this now, it will complain that JSON doesn't exist and OS doesn't exist because I have not imported those things. So let's go to the top and do that before we try running this. So we write import core encoding /JSON. That's where the JSON stuff is. And then we write import core OS. That's where the operating system stuff for writing and reading files is. If we now press F7, we see that our game is like this. And if we shut it down and then look inside the folder where our exe is, that we have a new level.json file here. We can just quickly inspect that one. It looks like this currently. It says something about platforms, and then it says a bunch of numbers, and this is one platform, this is another, and this is another. I like doing this where I first write it out and check that whatever it wrote looks nice, and then after that I can try to read that stuff back. So I write some dummy, some sort of throwaway data into there, which is my hard-coded standard level was written here when it shut down the program, because this code is run just before the program finishes, just after our main loop is done. After you close the window, this will run. A note here about the temp allocator is that when you're sure that you don't need anything in the temp allocator anymore, you can free everything in it. And the way you do that is you write free all context.temp allocator. This again doesn't really matter. I could have used the normal allocator here, because the program is about to shut down. Then I will get memory leaks reported by the tracking allocator. So I just prefer using the temp allocator and then freeing it here to avoid that. Now that we managed to write data into a file, we want to read it again back into the program when it starts, so that we can edit levels, quit the program, start up the program, and our stuff is still there. And the way we do that is that we scroll up here to where we create the level here. And I will just do this. I will remove this equals here and just remove everything here. So we just create a level. It's just a totally empty level. So what we will do now is that we will load that level.json file we wrote to the disk, and we will interpret the data in there so that it can end up back inside the level somehow. And we will do this by first reading the level.json file, the whole file, and we will do that in a similar way to at the bottom. So we will write if level data, comma OK equals os.read entire file. And then we say the file name, level.json, and then we use the temp allocator again, because this thing will read the whole, it will use a dynamic allocation to read the whole file in. And I don't care about this memory in the long run. I just want it during this if statement here, because the memory inside a file is not what I'm looking for. That memory will in turn get processed by the JSON stuff to be put into the level. So we've done the same funny thing here where we assign two values from the return value of os.read entire file, because this thing returns two separate values. So we put a semicolon here and write OK. At the bottom we had error here. If you compare, we had error because this one returned a enum, I think, that, or a union or something that contained an error message. What was the error? For read entire file, it just returns a bool. It's just like true if it went okay, false if it did not go okay. So then I used to use the word okay instead here, and then I check if it is okay, then in here we can use level data. So then we've read our file, we have it at hand. So now we can write if json.unmarshal level data. So unmarshal takes some JSON data and tries to apply it back into, for example, our level struct. So what we do is we type ampersand level here. So what happens here is that we take a pointer to the level variable here, and we send that into unmarshal, and it will read the JSON data that we loaded from the file, and it will try to apply that back into the level. Essentially, the structure of the JSON data has to match the structure of the struct. So the level struct looks like this, and if you look in the JSON data, it happens to contain a list of platforms like this. So then it knows like, okay, I can match up the name platforms with this one, and then for each value it sees that it wants a vector 2, and then it can match that up with a vector 2 just being two numbers essentially. So then it can figure all that out internally somehow. So we have an if here. So what I want to check here is if the return value of unmarshal is not nil. So if it is nil, then everything was fine. That means that the unmarshalling went fine. If it wasn't nil, then I just want to do some stuff here where I make sure that we actually have something to stand on in the level in case our level failed to load. So this is in case our level failed to load, we write append level platforms, and then we just write rl.vector2 and then -20, 20. This just puts in, because otherwise the level platforms list will be empty. So in case the unmarshal here fails, because it fails if the error it returns is not nil, then we do this. Another way that it can fail is if the file itself does not exist or wasn't possible to load, which is down here. So then we can write else here, and we can take the same code and copy paste it here. So now we just covered both cases here where it can go wrong. So now if we run our game, we see that we have a compiler allocator. Yeah, that's just a missing O there. We run it, then we have this stuff, and we can play some platforms, close the game, start it again, and our platforms are there because it loaded them from the file. And then again it saves it at the end and loads them on startup. So there you go. There you have some basic saving and loading of a level that we can edit while the game is running. Another quick word about this temp allocator stuff here is that the temp allocator, we free it at the end of the program here. The temp allocator is very useful also if you want to do temporary allocations during your main loop. Say that you want to make a string that is of sort of varying length that you want to put on the screen to write some data or something. Then you would often use the temp allocator to do that, because after you've written it to the screen, you no longer care about that data. So this is just a good thing to do, like in games, I would say, is to do at the end of your main loop here, just after end drawing, you take this line, you copy paste it and put it here. So then at the end of each frame, it frees the temp allocator. So then you're free to use the temp allocator inside your main game loop just to do any kind of funny allocations that you need to do. And you can just forget about the memory because it will get freed at the end of the frame. That's also a good way to avoid this kind of problem where you get these runaway memory leaks where you accidentally allocate data over and over and the memory usage of the program just grows and grows and grows. Instead, you can use, for all those cases where you actually do not need that memory to stay around for several frames, just always use the temp allocator. So if you use the temp allocator in those cases, and then you use a tracking allocator to find the leaks in all the other cases where you actually needed that memory to stay around, then I would say manual memory management sort of isn't that hard when you have those two tools. And I think that makes manual memory management less scary and sort of empowers you to use it. A final thing before we end here is actually a similar thing about memory leaks. You see, we load some textures here that we did in previous episode. Load texture there, load texture there, and there. You can unload these textures at the end here using rl.unload texture and then send in the texture variables there. That will free up the GPU memory. But again, it doesn't really matter because this memory that these textures use on the GPU will get freed when the program shuts down. It's just like before. If you have code that loads a texture just on startup and then uses just the one texture throughout the whole run of the program, that leak is not really that important. But if you create textures inside your main loop and do it over and over again, then it's very important suddenly that you unload them, because otherwise your GPU memory usage, because the GPU in the computer has separate memory from the CPU. That memory usage will grow and grow and grow until you run out of GPU memory, which is not very good. So that brings us to the fifth point here, the end of this series. Yes, this is the final episode of these Make Games Using Odin and Raylib series. However, it's not the end of tutorials on using Odin and Raylib on this channel. In the future, I'm thinking that I instead want to create self-contained videos with, say, here is like a 1-hour video where we create a whole little game in one style using, for example, Odin and Raylib. And then maybe I have another video where we create another game also using Odin and Raylib. The focus will most likely still be on Odin and Raylib, but I want to make maybe more self-contained videos like that. If you have enjoyed this series and you want to support me, then you can do so by becoming a patron on patreon.com, or perhaps buying my game Cat and Onion. There are links to those in this video's description. But yeah, thank you all so much for watching this series. I will see you around in upcoming Odin Raylib content on this channel. Bye bye.